let me record. Now I can record, okay. So today we are gonna discuss the rest of, I told you we're gonna take like one clean cut throughout almost all the topics that we will touch in the course. And then we will go back to each one of them in much more details, okay? So if you remember last time, the slides هي مفيش difference, it's continuation. ايه؟
نص السلايدز كانوا من اول
لا
يوم.
حطيتها لكم على البلاك بورد على السلايدز لحد اخر
بس you updated it.
I updated it, yes. So now you have a slides that goes all the way لحد نهاية introduction part, okay? So what we did last time is that we were looking at particularly the circuit switching case, and then we were looking at, or basically looking at a link scale, and then maybe it's a good idea to packet forwarding. So we look at the concept of routing and packet forwarding. So remember I told you earlier that when we do packet switching, what happens is a packet goes into the intermediate node. So the one that you see here is a packet, and it is going into the intermediate node. There is no reserved path from here to the destination. What happens is the intermediate node is gonna read part of the packet, which is the header part. That includes some address information that says that this packet is distant to some node over here, right? This intermediate node doesn't know anything other than some local information called routing table. This routing table says that if you see this destination address here, this is the link that you should send the data to. If you see this destination address, this is the link that you have to send the data to, and so on. So it says, and it's a pair input. So there is a routing table for this input, like this one, right? And there is, assume that this node can receive data from here as well. There will be another one that says if you receive from here and the destination address is such, then you should take it here. And if the destination address is something else, you should take it here. And if it's something else, you should take it here, and so on, okay? Now, that exists inside each one of those, as you see here, inside each one of those intermediate nodes, right? This operation of figuring out, right, how to build this table, so to figure out when there's a particular destination, what's the best next hub to send the data over, this is called the routing operation. Collectively, across the different nodes, this is gonna cause the packet to go through a particular path, which is route يعني طريق, right? So it will cause the packet eventually to go through a particular route until it reaches its destination. That operation of deciding how to fill the table, right? And then performing the switching, or what we call the one-step forwarding, right? This whole thing is called routing, okay? And the way to fill that particular table, which is something that we will study later in much more details when we come to the routing algorithms, right? Is called routing algorithm. It's some way that those guys learn somehow how to build this table. And this table is dynamic. So imagine, for example, that one of the intermediate links at some point is broken, just fails, right? Then all the nodes that are using this will have to figure out an alternative path, right? Otherwise, when they get information, they will have to drop it because there is no way to take it forward, okay? So this is a dynamic operation that gets affected by any change that happens in the network. You add a new node, you add a new link, one of the links fails, you remove one of the links, you update the speed of one of the links, right? Change the parameters of one of the links. That link was coaxial cable and then it became optical fiber, so completely different speed and different characteristics. Any such change should cause over the time a change of the routing table. How does that get built is something that we will learn later on, okay? Any questions about this operation, the routing and forwarding operation? Clear? Okay, we will have a few lectures on that later on, inshallah. Remember all what we have discussed so far in terms of calculating what happens during transmission was looking at a packet, and then when the packet is processed at a certain node, and then that's called the transmission delay, and then if it has to wait, because the input rate is faster than the output rate, we have something called queuing delay and so on, right? Now let's look at the other type of switching, the circuit switching, okay? This one does not care about packets, it actually cares about how much information I need to send, right? So what's the amount of total number of bits, not just a packet, but total number of bits that I need to send over a particular link, and then how much capacity is available on the link, okay? So the calculation here is absolutely different, okay? Remember, in this case, you have to reserve a path from the start to the end. Now, in this graph that you see here, it's trying to show you that a particular link is not necessarily reserved completely for only one circuit switch, okay? Maybe also if this node needs to communicate with this, it can also reserve part of this link, so maybe the last line, for example, and then reserve one of those empty slots on the other link. What do these empty slots represent? Many things. They can be many things. If this link, for example, is wireless, typically we divide the wireless into one of two dimensions or both. We divide over time, so we go for each one of those and we allocate a small portion of the time, and then the next, and then the next, and then we go back. So the first, the second, the third, the first, the second, the third, and they keep sending data only in their assigned slot. This is time multiplexing, right? Or we put the transmitted information over different frequency ranges, like what happens in your radio stations over your radio in the car, right? So there are multiple broadcasts happening. There is FM Qatar Foundation with, for example, some pop and jazz and stuff like that, and there is Qatar Quran radio, and there is Qatar radio, right? And they are all running at the same time, but the difference is you have to tune to one of them because they are using different frequency ranges, right? So again, each one of those could be a frequency range. If it's a cable, it can be that the cable has a certain capacity, like for example, it can transmit 10 megabits per second, but this guy requires only 1 megabit per second. So it's gonna take only a slot enough for 1 megabit per second and leave the others to whoever wants to use it. So these can be rates, right? Different rate allocations. Or they can be on optical fibers. Typically, one cable has multiple fibers. So that's actually an actual physical different link, right? Between this node and this node, there is one cable with, for example, 100 fibers inside. Each fiber can be reserved for a different stream of information, for a different information exchange, right? So you have to keep in mind that those links might be shared among different paths, different circuits, okay? So let me ask you a question. If I go through this link and this link allows, so assume that I connect from here, and this link allows me something like 10 megabits per second, right? That's the speed of this link. And this link is 3 megabits per second, and this link is 5 megabits per second, and this is 2 megabits per second, okay? And I ask you, what's the maximum speed that you can achieve on this circuit?
2.
Yeah, so always circuit switching is limited by the weakest link, right? This is the weakest one, this is the slowest one. So all your transmission is gonna be limited by this one, because despite the fact that this can carry 3 and this can carry 10 and so on, but you cannot push that amount on them because you will get congested and this is gonna be blocked, right? You can think of circuit switching like water pipes. If the water pipe allows a certain maximum pressure, if you try to push water more at a higher speed and more pressure, it will just break. It will not reach you, right? So you can think of this in a very similar way. In circuit switching, we forget completely that there are buffers here, right? So the buffers of the intermediate nodes are useful for packet switching. You can, because in packet switching we said, if this is a higher speed arrival rate of packets, and we have a slower service rate here, or slower rate here, then the packets will be stored in a buffer as much as the buffer allows until their turn comes, right? In circuit switching, there is no such a thing. What comes in has to go out. If there is no way for it to go out, it's not going to be allowed to come in the first place. Okay, so it's going to be blocked. Anything above 2 megabits per second is going to be blocked. It's not going to go through. Same here. Anything above 2 megabits per second is going to be blocked. Even though the input allows 3 and the output allows 5, right? But the overall circuit does not allow more than 2 megabits per second.
So how does like the computer, which is 10 megabits, know that the last one is 2 megabits?
Because when it reserves the path, there is a mechanism, those protocols that we talked about, right? When it reserves the path, it gets an answer that says you got a path and the maximum rate allowed of that path is this amount. You cannot do more. Okay? So that happens during the process of reserving the path. Okay? Or reserving the circuit in this case, as we call it. Okay? Okay, so this example is just meant to show you the sharing mechanism that I talked about, right? So if this link allows 1 megabit per second and you have a 10 kilobit per second, that's kind of a more statistical approach. That's not the deterministic that I talked about. So let's try to go through this and figure out how it happens. So assume, for example, that I have a link at the output here that allows 1 megabit per second, okay? And each user, when active, or we can say that the link allocated to each user is 100 kilobit per second, okay? But not all the users are active at the same time, okay? And that's what happens in reality. So in reality, for example, when we use the landline, okay, if we think that all the users are going to talk all the time, so they will try to reserve circuits all the time, most probably out of all the phones in a particular district, only 100 will be connected, and the rest will always get a busy tone, right? But that's not what happens. I want to talk at some point, other people want to talk at some other point, so there is statistical aspect, or there is randomness on when and how long each one wants to talk, right? So the same here, user can be active 10% of the time. So the probability of a user wanting to connect is how much?
1 kilobit.
لا. Probability of wanting to connect, probability. Probability of active. If the user is active 10% of the time, then the probability of active is equal to 0.1. Is everyone getting this, يا بنات? Okay, if I tell you, I mean, if you're not getting this, if everyone is getting it, no need to explain further. Anyone confused where we got that 0.1 from? Or what does it mean? Clear to everyone? خلاص, move on. Okay. If you are not clear, say it. Okay. So the probability of active for any one of those users is 0.1, 10% of the time, and the remaining 90% of the time the user does not want to send anything. Okay? And that happens randomly, so it doesn't mean that each user is going to take the first second and then stay silent for the rest of the 10 seconds. No. Each one of them can decide to be active at some random point, and the probability of that happening is equal to 0.1. Okay? Okay. And now let's look at if I use circuit switching on this link. Okay? Circuit switching means what? I will reserve a full path, right, for each one who wants to talk. How many I can support simultaneously? Simultaneously, and at the same time, how many?
الباث اللي هو فيه 4
Hmm?
الباث فيه 4 lines.
لا الباث يسمح 1 megabit per second. We define the path هنا using the capacity of that path. So the path here, the link here allows 1 megabit per second. Each one of those, when it's active, it wants to send 100 kilobits per second. Okay? The question says, if each one who wants to talk is going to use circuit switching, how many this link can support at the same time? How many?
10 times.
10, right? Where does it come from? We don't care about this number now, because we are looking at when they are all active, what will happen, right? Assuming that they are all active, how many I can support? We can see the maximum capacity is 1 megabit per second. Each one requires 10 kilobits per second, then
So 0.5.
divide 1 mega by 10 kilo, that tells you that 10 users can transmit at the same time. If an 11th user tries to get in, he or she will find the network blocked, cannot get into the network, right? That's for circuit switching, okay? Now let's look at packet switching, okay? Assume, for example, now in packet switching, you don't know, because in packet switching, you don't know exactly when they are gonna send the information, and also you are not reserving anything for anyone. Whenever you get a packet, you will try to find a way to send it through, okay? The problem here is, okay, when the network is gonna be blocked, okay, is when there are 10 or more. As we know, each one of those is 100 kilobit per second, right? So the network is gonna be blocked when 10 or more of those users, when more than 10 of those users wants to transmit. So we want to avoid that situation. But let's see how often does this situation happen, to see how circuit switching is gonna be more efficient, okay? For packet switching, how packet switching is gonna be more efficient. For circuit switching, you will just go when you plan your network and you will say, because they can all talk at the same time, then when any one of them talks, he's gonna take the network completely for him or herself, then I will make sure that this is not connected to more than 10 users. Just 10 users and that's it, because any other extra user will not find space on the circuit to connect, okay? Now for packet switching, that's not the situation. Maybe I can connect 35 users, right? And how do I calculate the quality of my connectivity in this case? I want to see how often. I know that 35 users, if they try all to talk at the same time, they will not be able to do that. Only 10 of them will be able, right? But let's see if this happens a lot or it happens just very, very little time. And most of the time, everyone who wants to connect now will find something available, okay? How do we do that? If I have 35 users, I want to find the probability that more than 10 are active, okay? معلش دي وحشة شوية عشان رايحة ناحية ال probability and statistics course. I have 35, yes, and I want to find the probability that I have 35 trials, and I want to find the probability that more than 10 trials or more than 10 successes. Remember what was the distribution that defines this? Something called the binomial distribution. You remember the name when I say it differently. But probably you don't like the math. It doesn't matter. I'm not even doing the math here. But if you use, because you can always, in this course, I'm not asking you to perform the math. Just understand the concept, okay? So the concept says that I want to find how often, so what's the probability that out of 35, 10 or more more than 10 will talk at the same time. Because that's the case, if it's 11 or 12 or 13 or 14, that's the case where some of the users will find that the service is failing, right? So I want to know how often does this happen. So I want to find the probability that the number of connected users is greater than 10. If you go to the binomial distribution, and by the way, if you want to calculate something for this, just go online and say binomial distribution calculate. And then you give it what's the total number of users, how many trials you want, like this number or more, right? And then say calculate, it will give you something around 0.00042, I remember. It was not just 4, 2, but if you take it up to 4 digits only, that's the probability. You see, it happens really out of 1,000 times, there's 4 times only, this is 1,000, it's 10,000. Out of 10,000 times, only 4 times that I might have some user that will not be able to connect. Right? Yes. So I can actually connect, maybe for this network, I can connect 35 users because what? 99.96% of the time, all the users will be able to connect. And only 4 out of 10,000, one or more user might call me and say, oh, I was trying to connect and it didn't happen. And if they stop and try again, it will happen. It will work for them, right? So that's really, because when we work with networks, We cannot guarantee the service 100% of the time, but as long as we guarantee it most of the time, with very high probability of success and very little probability of failure, we can say that our system is a high quality system, okay? It will happen every now and then that you raise your mobile phone and you cannot find a signal, right? But if it happens like most of the day, you will hate that carrier, okay? But if it happens maybe 1-2 minutes every other day, it's okay. I will just move away until I get the signal back and do my call. So it's a little bit of delay that happens every while. But if it happens very repeatedly, then your perception as a customer is that this network is not good. It doesn't work for me.
So when I
Okay.
start the call, this is when I take a path, or the path is already there reserved for me?
You're not taking a path here. What happens is when you start a call, because this is not a phone call, it's a packet switching, so it's not circuit switching. Phone calls are circuit switching. So packet switching, when you start, you are just sending a packet, and your packet gets through. So if I have 35 users, the chances that one of them wants to send, one or more of them wants to send a packet and it doesn't get through immediately is less than 5 out of 10,000.
What's a realistic example of packet switching?
Everything that you do except voice calls. So when you send emails, when you browse a website, when you watch a video on YouTube, all of these are packet switching. Okay? Only classic voice calls, and even in the 5G, part of those classic voice calls is actually voice over IP. If it's over IP, it's packet switching. Okay? Any questions here? Okay. So there are 2 questions here, just to remind you. How did we get this value? By looking at this problem, we figured out that this is a binomial distribution, and then you can calculate the binomial by any calculator or anything, okay? And the second question says, what happens if I get more than 35 users? So instead of that, so we did this, assuming that we have 35, and then we calculated the probability that one or more of them is not gonna be happy, right? Which is the probability that out of the 35, more than 10 will try to send packets at the same time. So what if this number increases? What do you expect for this probability?
Just scale it by the same factor?
Just the question, you cannot figure out the scale, but the question is gonna increase or decrease, that's the question, yeah. So if you increase the number of users, intuitively, this means that there are more chances that they will block each other, right? So this probability is gonna increase, okay? That's it for this slide. Any questions? طيب. So this slide shows you that what we did in the previous calculation really shows that packet switching is very nice, okay? And it works very nicely, okay? But it has its issues, right? So it's not really the winner all the time. Yes?
Just before we move on, where did we really just get the value 0.0? It's binomial, but like if you ask me an exam, how do you get it? How do I get it? Will you give me the table or something?
If I ask in the exam for what?
To
For
get
the
value?
0.0004?
Yeah.
I'm not gonna ask in the exam. Don't worry. It was just an illustrative example, okay? This slide is actually looking at whether what we looked at in the previous slide says that it's always the case that packet switching is better than circuit switching, and the answer is no. Can anyone figure out why? What's the problem with the approach that packet switching uses? Why we keep voice calls until today over circuit switching, not packet switching? Can anyone figure out? When we did the circuit switching, remember our calculations was, did we use any probability? No. When we did the packet switching, we had to use probability, right? So what do you think is the problem with the packet switching? So even though it looks like I can put more users on the same link capacity and they will perform well, but what's the probability? What's the problem? They will perform well from what we calculated, but there's another aspect that they might not perform well on. What is it?
Does it like have to do with something in between getting blocked and causing conflicts?
Yeah.
Maybe the message will not, the other user will not receive the message.
Okay, so there is a chance that they
You will
can
not
get
the
blocked,
message.
right? Or,
Is there a possibility like
remember what we mentioned, yeah?
one message like would
from one to another would be delivered to some other.
No, that's a totally different, because that also, that can happen in circuit switching if I figure out the path incorrectly. So that's a different problem. But remember what I mentioned, right? When we tried to look at packet switching, we were doing everything in a randomized way, in a probabilistic way, right? We have no guarantees. Even though the probability is small, that small thing can sometimes happen repeatedly, right? Not only that, remember in packet switching what happens, okay? The packet goes to the node decides which way is gonna be next. And I told you last lecture that it might happen that two packets coming from the same source, going to the same destination, can take two completely different routes, right? And then probably one of those routes is gonna be longer than the other. And if it is longer, it means that the packet is gonna be delayed more than the other, right? So there's no guarantee that things are gonna be delivered in a nice, uniform way. And for voice and video, this is highly needed. For data, there is no problem. When you are sending an email, you are just looking at the email as a whole when it arrives. You are not looking intermediately how many lines arrived quickly and how many lines arrived slowly. You just get the email. In between, what happens does not affect you as a user. But when you are talking to one over the voice, or you are video conferencing with someone, and then all of a sudden they are moving, and then they get stuck, and then they move suddenly, right? That's bad quality. Why this happens? Because packet switching might make some stuff arrive faster, some other stuff of the same video arrives slower, so it gets stuck. And then when they arrive, it moves quickly, right? So having that jitter, this is called a jitter, is not acceptable in continuous services, particularly interactive ones like the voice and the video. So that's why in voice and video, there is an emulation of circuit switching. So the network tries to work in a circuit switch mechanism rather than a packet switch mechanism to guarantee that things will arrive uniformly on time, okay?
Circuit is more expensive than packet, right?
No, it's not more expensive. It's it can utilize the network in a way much less. So for circuit switching, for the same network that has 10 megabits per second, to guarantee full circuit switching, you can only accommodate 10 users, right? For packet switching, we saw that up to 35, you can still accommodate them. Most probably, if they are not using one of those killer apps, like the video or the voice, if they are using any other data, they will be happy, okay? And even for video, and the probability of this happening is very low, so most of the time their video and audio is going through nicely, okay? So no, the advantage of packet switching is that allows you to utilize the network in a better way. So you can put more users on the same network, okay? Per the same capacity. But the disadvantage is that it does not guarantee timely delivery and uniform organized delivery, right? And so sometimes you need circuit switching, sometimes you need packet switching, okay? Okay, this slide is just talks about the internet that we looked at. It's kind of more of a philosophical slide. So it just says that, remember when we talked about the internet, we talked about the access ISPs, the ones that are like regional or local, and then the global ones, we call them the core ISPs, right? And the network itself is divided into core and edge, or core and access system. And then the evolution of the internet when it started, and you can see that when you look at the last few slides. I'm not going to address them in the class, that talks about the history of the internet, right? It evolved, right? One era after the other due to economic factors and policies, national policies factors. So some nations were pushing this to move forward, some nations were more restrictive. Then an economic need came because it provides lots of services that can enhance the economy. That was another pushing factor, and so on. So the reasons why it evolved in not a very steady way, or was not designed from scratch to be exactly like what we see today, is that it was an evolution process, and this was pushed by economic and political factors or national policies, okay? That's just a philosophical, okay. Given millions of access ISPs, how to connect them? This is a slide that tells you that even though we talk about the internet, which is connected globally now, it's not really that every single point is connected to the other. This would have been a massive way of doing it. So something that looks like this, and it would have been really extremely uneconomical. Okay? So imagine with all those nodes that we have, each one of them has to be connected to all the others. This is going to take infinite cost. Okay? You cannot do that. Okay? The ground is going to be digged all the day. There will never be roads or anything. It will just be jumping across construction sites. So that's one issue. The other issue is the amount of material that you need to do this is going to be massive material. Whether it's optical fibers or copper cables or even wireless connectivity, okay? And the way we calculate how much or how many connections are needed in this case, we will study that when we look at network graphs. But anyways, in this case, the number of needed links is going to be in the order of square the number of nodes. So calculate the total number of nodes over the internet, take that number, square it, that will tell you roughly how many links you need to connect every single node to every other node, which is not happening. So how do we do that? In that evolution process, it's a concentration and a connection of networks together. So we start by a global ISP, right? But then again, if we want every single node to be connected directly to the global ISP, this is going to still be a massive connectivity. Not only that, that global ISP is going to make a lot of money. So because that global ISP is going to make a lot of money, other people who have money will say, okay, I'm going to do the same like him. So I'm going to be also another global ISP, right? It's similar to when you live in a particular فريج يعني أو district أو حي, and then you have a very successful grocery store, and then the next day another grocery store opens across the street because it sees that there is a business, right? So the same. So maybe the idea started with one global, was typically in the US, and then everyone saw the success. So we ended up with many ISPs trying to replicate the same thing. Each one of them, because of regional policies, got the ability to use his own geographically co-located customers to be connected to that ISP. So we ended up with many scattered ISPs, but the problem here is that they still need to interconnect with each other, and then the evolution was to interconnect those through something called the IXP, the Internet Exchange Points. These are massive routing and switching devices that connects the big ISPs together, and then another evolution was the appearance of more smaller regional local ISPs. Those guys, the regional net guys, the yellow ones that you see here. This is similar to Ooredoo, for example, or Saudi Telecom, or Orange in Egypt, or whatever. And then the core ones, and then those core ones have connected together. Why did they connect together? Why did it not just stay in separate islands? Because of the economic factors. They need the connection to the other market. They need the connection to the other geographic location. So that's why, even though they are competing, they decided to connect with each other. Okay. So that just tells you the story. There is one layer above this that has to do more of services. The global players that are providing very high level of services. Examples of those are Google, Microsoft, right? Those big guys, they were not originally internet service owners, right? They were just providing services over the internet. With time and with the growth of their services, they became themselves owner of some of the infrastructure of the internet, okay? So they own their own ISPs and to provide their services over it, okay? So that's what we ended up right now. We have the regional, we have the internet exchanges connecting the different ISPs, and we have also the service, the big, massive service providers appearing at the same level at the ISPs. They have their own infrastructure completely owned by them, and it's connected through the rest of the internet. They are not putting their stuff on the infrastructure of other people. Yes?
What's IXP and ISP?
Internet service provider, the ISP, the one that you go to provide you with connectivity to the internet. IXP.
So Ooredoo? Ooredoo?
Ooredoo, for example. Okay. IXP is not an entity. It's devices that are supported by different ISPs, whether they are access ISP like Ooredoo, or something very large like, not Vodafone the local, but Vodafone in Europe, for example. Vodafone in Europe is a massive provider of internet connectivity to European countries and Middle Eastern countries, right? So that's ISP tier 1, okay? This provides internet connectivity to other ISPs, okay? And those big guys and the other ISPs are connected by big exchanges. You can think of this as shared resource. I pay part of the cost, he pays part of the cost. So that will get connected together, okay? So it's not owned by one of them, but by both parties, okay? And then this is called the internet exchange points, okay? And on top of that, the service providers now own their own routers, storage devices, cables, and everything, similar to, for example, Google and Microsoft, because they need massive infrastructure for their applications. So rather than working on the devices of other ISPs, they have their own infrastructure as an ISP, but they don't provide service as a network provider. They provide service as things like computation, storage, the things that you get from Google, right? You don't go to Google and say, please connect me to the internet, right? You go to Google and say, I want to use your machine learning computation infrastructure like Colab, Google Colab, or you go to Google and say, I want to use your search website, or you go to Google and you say, I want to use your Google Drive, Gmail, right? All of these are massive services provided by this service provider, and it falls within their own devices. They are not using other people's devices for this service. And that's the overall global picture right now. Okay, so maybe another global ISP is something like Sprint in North America, okay? So this is just a picture now how it's getting more and more complicated. So I think we are done with this part. So remember when we looked at this problem earlier, why you have this?
الريكوردينج بعد ما كمل.
لا ريكوردنج شغال، بس هو انتوا هنا شايفين حاجات غير اللي انا شايفها. Okay, so remember we had a discussion about this situation earlier, and we mentioned the situation where you have more than one input link to a particular intermediate node, and they are working at collective speeds that are higher than the speed of the output link from that node. And then we said that this might cause the packets to stay inside until their turn comes, and we call that queuing delay, okay? So until now we have two types of delays. The delay that happens because when I'm sending a packet, I need to send the whole thing, and if I'm sending this using a particular rate, so number of bits per second, and I have total size for the packet, then the full transmission of the packet is going to take some time. I call that transmission delay. And the amount of the time that the packet has been waiting here until its turn comes to be sent out, that's called queuing delay. So we have two types of delays. Before going through the other extra type of delay, there is one more thing. Definitely any device will not have an infinite memory, right? So in order to store those packets coming in, I must have some memory of a particular finite size. I'll be able to store, but if the rate difference here is really big, at some point, this is gonna fill up. When it fills up, what will happen? I still need to send some information, so I will keep sending it. There is no way to store it here. What will happen to that packet or to that information? It will just be lost. There is no place to store it. There is no way to push it forward because there is a lot ahead of time. Then what will happen is that the packet will be dropped, will be lost. This guy thinks it is sent. This guy was not able to take it forward because it was not stored, so it's lost, right? It's as if someone comes with a letter to your home, you are not there, they leave the letter at the door, you come back after 1 year, what will happen to the letter? It's degraded, it's no longer there, right? It just disappears. So that's dropped, totally lost. Or someone will come and think it's garbage and collects it and throws it into the garbage bin. So the letter is lost. Similarly, the data here is going to be the packet is going to be dropped. So two things can happen. Either it can be delayed in a queue, and then after that it will be transmitted. So that's a delay situation. Or the other thing is that it's not going to be transmitted in the first place. Just completely lost. We call that dropped. So there are two measures that measure those two factors. There is the delay, we mentioned that already earlier, okay? And there is something else that measures how much information is successfully transmitted over the link. We call that the throughput. So we have two measures of network performance. One of them is called delay, and that's calculated in seconds or minutes or whatever, right? So it's a time thing, okay? But the delay has many different types, as we have seen so far, two types. And there is something called throughput. O-U-G-H. So there's one U missing in the middle. T-H-R-O-U-G-H. Okay, that's calculated by packets per second, or it can be bits per second, okay? But this is not just the regular capacity that we talk about. This is more focused on how many are successfully transmitted, okay? Because remember that there are some stuff that we will try to push, they will be lost. So in that case, the throughput is not just simply what I push in, it's actually what successfully gets out, okay? That's called the throughput. We have, again, later on we'll revisit those concepts in much more details, and we will know how they can be calculated as well, okay? Sometimes the opposite of the throughput, they call it the loss. So if you are more focused on how much you are trying to get in, but it never went through, then you calculate something opposite to the throughput. That's called the loss rate, or the packet loss rate, okay? The number of packets lost per second, or the number of bits lost per second, okay? Going back to the delay, we will find that there are two other types of delays. One of them we discussed earlier. We said that whenever you have some data going into an intermediate node, after receiving the full data, the intermediate node needs to read some information from that packet and then take a decision based on that. This is a processing time. So there is, in addition to the transmission time, what was the equation for this one? Length of the packet divided by rate of transmission, okay, of the link, okay? And we have also the queuing. We didn't study an expression, but we know where it comes from, that the packet might wait for others to be processed ahead of it, because the arrival rate, for example, at some point is higher than the service rate. Okay? Why am I saying at some point? Because in reality, you will not design a network where the arrival rate at some point is greater than the other, because you know definitely that this is going to cause losses. Okay? So you will not allow this. You will design them to have an arrival which is smaller than the service, okay? But since this arrival happens randomly, at some point you might have a bunch of arrivals at the same time. So it looks like the rate increased. So the average rate is still here, smaller than here, but at some point they might crumble, right? And then they have time to be serviced, okay? Because no more arrival is coming, so the queue is not going to build up forever, okay? And you can imagine this even when going to the bank. The teller might be really servicing people at a very nice rate of 2 minutes per person, for example, okay? But unfortunately, over the first half an hour, 100 people arrive in just 1 half hour, okay? And then after that, you stay for a couple of hours, nobody's coming until another person comes. So the average from the arrival is going to be less than the service rate, but because they crumbled in, there's going to be also queuing. It's not going to be just service and that's it, okay? So anyways, those are the two types, the queuing and the transmission. We discussed those. The processing, we mentioned it earlier and I mentioned it today. Whatever you need to do in order to perform your own operation as an intermediate node. You need to read some information, take it and do some calculations, and then based on that calculation, you decide that the packet should go this way, that way, or stay a little bit or whatever, okay? So that's called processing time. What remains is, we know that electromagnetic signals, whether they are going through a cable or they are going through the air, they don't just travel instantaneously. If I send some information from your phone to that access point, it doesn't really arrive. It arrives with the speed of light, so it doesn't arrive with an infinite speed. It takes some time, even though it's very short, but sometimes over larger distances, it can become a countable time, okay? For example, in satellite communication, that time is there, it's in milliseconds. It's something that at some point you can feel, okay? So that's called the propagation delay. The time it takes the signal to travel across the medium, okay? That's the last type of delay. So we have 4 types of delays. 3 of them are more or less related to the node itself, and the 4th is just related to the distance between one node and the next one. Okay? All the other 3, processing is a property of the node, queuing is a property of the node and its input ports, output port speeds, right? Transmission is a property of the node related to the output port speed, right? But only the propagation delay is related actually to the distance. It doesn't matter how fast, in terms of data rate, the link is, the distance has to do with the speed of light. Because these are all electromagnetic signals traveling from one point to the other. Even inside cables, they are electromagnetic signals, okay? And I don't know if you know about the channel called Veritasium. It's a very nice channel, talks about physics and stuff like that. And he has one of his videos where he shows that even though in electricity we think it happens instantaneously, this technical electricity, but he shows that if you have a long enough connectivity between the point where you switch the signal on and off and the lamp that's going to take that electricity and start producing light, if you make that long enough, you see that he shows it in the experiment, you close the switch and then a little bit of a pause until you see the light coming on. Okay? Even though we tend to think that electricity appears immediately, it doesn't. Even that 50 hertz electricity, it still takes time to travel, okay? Okay. And this is meant to give you a feeling about the queuing delay. Again, we didn't really talk about how to calculate that, but we know that if, generally speaking, the amount, so here we have L, the length of a packet, we have R, the speed of processing the packet at a particular node, and we have A, which is how many packets are arriving on the average per second. It's the rate of arrival of packets. So when you multiply L by A, you get the rate of bits arriving, right? You divide that by R, the rate of servicing the bits, and this gives you a factor which is called traffic intensity. We call that factor the traffic intensity. If that factor is very, very, very small, close to 0, then you can actually ignore the queuing delay completely. So if the rate of arrival is much smaller than the rate of service, then you assume that the queuing is not going to happen. Every time someone comes, right, almost certain that he or she will find an empty teller and they will go directly to service. No waiting in a queue, okay? Now, if that number is not very small, but still less than 1, then you will have some queuing delay, which can be a large number, depending on how close this number is to 1. Still, the arrival rate is less than the service rate, but because of the randomness in arrival, queuing will still happen on the average, okay? So you will have some finite queuing time in this case. If the arrival rate is larger than the service rate, the queuing time will build up until it reaches infinity, right? People keep coming, the queue keeps getting longer and longer, and the service is not keeping up with them. Okay, so that's where, for example, when you are at the cashier at في الجمعية مثلا في ميرا ولا في كارفور ولا any one of those, and then they have only 2 cashiers and people start arriving and the queue is getting longer, and then all of a sudden you see the floor manager calling more people to come to the cashier because they don't want this to build up, and then people will probably just leave the items and leave the store, right? Because it's going to be crazy, okay? So again, if the arrival rate is larger, if this division is greater than 1, that's an uncontrollable system. That's an unstable system. That's a failing system, okay? Okay. Okay, this tells you that you can use this command, by the way, if you have a computer. I don't know if you can figure out how to use it on the iPad, but this is a very nice command to try to play web on your computer. It works with Windows, and it works with Mac, and it works with Linux. It's every one of them. And if you try to put that command in, it will give you actually a statistic about every single link, right? Between every two nodes from the source that you define until the final destination. So if you say, for example, trace route from, you are now at Qatar University, so from qu.edu.qa, right? And then to google.com, right? Now this takes multiple intermediate nodes until it reaches one of the Google servers, right? It will show you a line for each one of those links until you reach Google. And for each line, it will give you the delay over that line, okay? And why it has three numbers? Because it tries to give you something like to get an average out of. So rather than just sending one packet and calculating the delay, it sends three consecutive packets and tells you that the delay over those three is those three numbers, okay? So it's very nice to play with if you want to look at it. And sometimes, notice, for example, here you can see that the delay is much larger than the other ones. So here we are talking about tens of microseconds. All of a sudden, we went into hundreds of milliseconds, sorry, okay? Why? Because these links are very long links across Atlantic, for example, or across the Mediterranean, and so on. So those ones have larger delays across them, okay? By the way, those delays that I showed you in the previous slide, you think they are which type of delay? Is it, yeah, which one of those four?
Depends on the website. Because, for example, in Arab Cup and all that, when you want to enter to a website, there's a queue there.
Yes.
So that is queuing.
Yeah. So what you are trying to say is that the value will depend on the most dominant number. But this implicitly says that it's calculating all of them, which is the case. It's actually calculating all the delays. We call that the total packet end-to-end delay, okay, from one point to the other. Which one is more dominant now depends on the scenario, right? Sometimes the queuing is the most aggravating factor. Sometimes when he points here to some links and says that these are cross-Atlantic links, he's assuming that those are connected to servers that are not really that queued, the intermediate node, but more it's a propagation delay. It's the length of the line and so on. But in general, it's providing you with the sum of all those four, okay? And your answer was more implying this, but you were trying to focus, to say why it gets larger at some point, because one of the factors is more aggravated than the others, yes. Just, I think I already described this. So what happens to cause packet losses, right? So there's not that much information here. And then we have what's called throughput, and I described this to you as well. You don't need to calculate it right now because the way to calculate this will come later, but at least you need to know what's a throughput, what does it really measure, okay? So we have been through that as well. And I'm assuming that we will stop at this point. So that's another example of throughput and discussing the bottleneck. When you have a slower link, the slower link is the one that controls the performance. And here it shows this in a more aggravated way. So if too many links are connected to a link which is even much faster than them, but because they are all sharing it, this might become the bottleneck, right? Because for example, if we say that each one of those rates is 10 megabit per second, and we have 1, 2, 3, 4, 5, 6, right? So we have approximately 60 going in, right? 10, 10, 10, 10 added together. So we need at least 60. If this has a total capacity of 40, then it becomes the bottleneck. Even though as an individual link, it's more than each one of them, but the reality is because it's shared among them, it becomes the defining bottleneck, okay? So the bottleneck is not just simply by looking at which link is slower and that's it. Also, you have to consider which links are shared, okay? That's very important when you are looking at calculating the bottleneck. I will stop here. That's a very good stop.